In this video, we're going to look at the chromatic polynomial. And so this is helpful in determining our chromatic number. Here, we define formally the chromatic polynomial. If g is a graph and x is a natural number, we let pg of x denote the number of ways to properly color g with x or fewer colors. This pg, this is a polynomial function of x, and we call it the chromatic polynomial. So we're going to look at several examples. So let's say we have a relatively simple graph here. If we wanted to color this with x colors, this first vertex in the top left, we have x ways to color it. Right next to it, we can color this with any of the other colors other than the one that's right next to it. So we have x minus 1 colors, or x minus 1 ways. This next one also has x minus 1 ways. It cannot have the same color as this one, but there are x colors that are x minus 1 colors still open to it. And this one right here has x minus 1 colors open to it. It can't have this one. And so our polynomial, our chromatic polynomial, pg of x, it is given by x times x minus 1 times x minus 1 times x minus 1. This is the total number of ways to color the graph with x colors. The smallest number of x such that pg of x is not 0, that is chi of g. So notice if we were to plug in 1 here, that would zero out this polynomial. If we plug in 2, it won't zero out the polynomial. And so if our value of x is 2, we end up with 2 times 1 times 1 times 1, which is 2, which is not 0. So 2 is the smallest value that is not 0, the smallest integer value of x that we could plug in that's non-zero. And so that tells us that the chromatic number of this graph is, in fact, 2. If we were to look at the chromatic polynomial for our discrete graph on n vertices, a discrete graph on n vertices, again, is just n distinct points. So you would have x values open for any of those, and so that polynomial is just going to be x to the n. Because that polynomial is x to the n, you end up with the chromatic number for a discrete graph on n vertices is just 1. You just have a bunch of discrete points with no edges between them. If we have a complete graph on n vertices, everything's connected to everything else, so you have x minus 1, x minus 2, because this one can't have the color of either of the previous two, x minus 3, and so on. And so when you look at that, you end up with this polynomial of x times x minus 1 times x minus 2 all the way down to x minus n minus 1. Right, so If we have a complete graph on n vertices, we have x minus n minus 1 points, options remaining for that last one. And so the chromatic number for that complete graph is going to be n itself. Everything has to have a distinctly different color. If we have a linear graph on n vertices, we'd have x, x minus 1, x minus 1, so on and so forth. Oh, actually I take that back. Whew. Just x minus 1, x minus 1, x minus 1. And so our polynomial, chromatic polynomial, is x times x minus 1 to the n minus 1. And our chromatic number is simply 2 itself. Fantastic. So this feels pretty straightforward. So let's look at a complete graph, or not complete graph, a cycle on 4 vertices. So here you have x options. Here you have x minus 1. Here we have x minus 1. And here, well, it might depend. Right? So it depends on whether or not this color and this color received the same color. Because they're not next to each other, they did not have to, but we have two different cases, really. Right? So it could either be x minus 1 or it could be x minus 2, depending on whether this color here and this color here got the same color. Because of that, our polynomial, our chromatic polynomial, is going to be the two polynomials added together. So what I mean by that is you could have x times x minus 1 squared, nope, not squared, cubed, or you could have x times x minus 1 squared times x minus 2. Those are really the two cases that we have. Case 1. Case 1 is the case where the color on this and the color on this were the same, so then this one has x minus 1 options. And case 2 says, oh, but what if the color here and the color here were given different colors? Then this one has two colors it has to avoid out of the x available to it. So those are our two cases. As we continue looking at that, if we were to think about a disconnected graph with two components, G1 and G2, if we wanted to find out what is that chromatic polynomial, it is the product of those chromatic polynomials. You can use the fundamental counting principle, the way one component is independent of the other, and so that's what we end up with. It's just the product of those two polynomials. So here, as a quick example, if our first graph, G1, looks like this, and our second graph, G2, looks like this, then the polynomial associated with G1 is x times x minus 1. The polynomial associated with G2 is x times x minus 1 times x minus 2. And so the polynomial associated with that graph, this disconnected graph G, it's going to be x times x1, x times x minus 1 times x minus 1 times x minus 2. So writing it compactly, you have x squared, x minus 1 squared times x minus 2. Simply taking the product of this piece with this piece. Great. All right. In our next video, we will just real quickly talk about quotient graphs and a reduction theorem. So we will see you there.